Welcome to BMAC.MATH tutorial. Subscribe to our channel for freshly uploaded content. This is a question from linear algebra which had been given in CSI and NET 2019 December session. We are given C01 and a function defined on the space C01 cross C01. We will check the validity of the given three conditions. We know that a function is an inner product if it satisfies certain conditions. UV, inner product on a vector space V, UV is equals to VW is equals to VU. Number 2, U plus V comma W is equals to U comma W plus V comma W. CUV is equals to C U comma V. UU is greater or equals to 0 and UU is equals to 0 if and only if U is equals to 0. For all UVW in the vector space V and a scalar C in the underlying field say K. And also this function is said to be a bilinear form if the function is linear in both U and V. That is, number 1, U plus V comma W is equals to UW plus VW. Number 2, CUW is equals to C times U comma W. This gives linearity in the first variable and also linearity in the second variable. V plus W is equals to U comma V plus U comma W. U comma lambda W is equals to lambda U comma W for all U, V, W in V and C and lambda in the underlying field say K. Here our vector space is C01 and the underlying field is the set of real numbers. We will check these conditions one by one. First of all, we see that if fx is equals to minus 1, then angular brackets f comma f is 0 to 1 ft gt whole square dt. 0 to 1 minus 1 into minus 1 square, which is equals to 1 dt, and hence 0 to 1 minus 1 dt, which gives us minus 1, which is not greater or equals to 0. Thus, this need not be greater or equals to 0 for all f in C01. Hence, this axiom 4 is not satisfied and this function is not an inner product space. An inner product. For the bilinear form, let we will check the third axiom. Let fx is equals to 1, gx is equals to x, and hx is equals to 2. Then f, g, h are all continuous functions. Now we will see that if this happens, this is equals to f is 1, g is x, h is 2 whole square dx. X square plus 4x plus 4 dx is equals to 0, 1 x square plus 4x plus 4 dx, which gives us x cubed by 3, 4x square by 2, that is 2x square plus 4x 1 by 3 plus 2 plus 4, which gives us 3, 1 plus 6 plus 12, that is 12 plus 7, 19 by 3. Angular brackets f comma g is equals to 0, 1, f is 1, g is x dx, 0, 1 x dx, which is x square by 2, and it gives half. Sorry, it should be x square, x cubed by 3 and 1 by 3. Angular brackets f comma h is 1, h is 2, and hence h square is 4. Thus 4, which is 4, plus angular brackets f comma h is equals to 1/3 plus 4, giving us 12 plus 1 by 3, which is 13 by 3. Thus angular brackets f g plus h is not equals to f g plus angular brackets f h, and hence this is not a bilinear form. We have found that this angular bracket is neither a bilinear form nor an inner product space. Thus, we check the options. Number 1 tells that this function is an inner product space. This is ruled out. Number 2, this is a bilinear form on C01 but is not an inner product space. This is also ruled out since this is not an inner product space. Number 4, angular brackets f comma f is strictly greater or equals to 0. This is not true, as we have seen with an example. And number 3 is the only right answer.